Intermolecular attractive forces. When we are dealing with ionic compounds do not have intermolecular attractive forces. Remember, ionic compounds have a crystal lattice structure. Looks like a big connects or tinker toy structure with alternating positive and negative charges that are attracted to each other by strong electrostatic charges. But when we're dealing with molecules, when we're dealing with covalent compounds, we're dealing with a situation, for instance, where we have these individual molecules. Now I'm not going to give this any kind of a name, but I'm just going to say, let's just say these are molecules. Yes, the atoms that are inside that molecule are being attracted very strongly by covalent bonds, kind of like your head and your arms attached onto your body. So those are very, very strong covalent bonds. But between people, for instance, or between molecules, what we have are relatively weak intermolecular attractive forces. And that's what that red stuff, if you will, in between those consists of. And those intermolecular attractive forces between the molecules are responsible for whether a compound is, among other things, whether it's a solid, liquid, or a gas at room temperature. So it gives it some of its characteristics. Now there are three main types of intermolecular attractive forces. The first of these is called the London dispersion forces, sometimes called induced dipole, and also known as van der Waals forces. And of course, in the AP world, we hear all of them, but I would say London dispersion forces are becoming more and more the term you're going to hear this referred to as. Now, London dispersion forces is the weakest of the attractive forces, as it says down here. All covalently bonded substances are attracted by at least London dispersion forces. Now, let's look at what's happening here. Let's say we have two atoms. Let's say we've got two atoms of xenon. Okay, so here's a nucleus, and then around that nucleus we have the electron cloud, and it's fairly spread out here. And then along comes another xenon, and it's got this kind of spherical, nice electron cloud around it. And so you have these xenon atoms getting close to each other. Now remember, inside there, that nucleus is positively charged, and then all around out here in this electron cloud, we have these interspersed negative electrons out here in the electron cloud. At any given moment in time, one of those electron clouds might get distorted. And if it did, you would have maybe more electrons shifting to one side or the other. If that happens, what we end up with is a situation where the positive nucleus of one of the atoms is attracting the electron cloud of the other atom. And we get a distorted or polarized electron cloud. This is what it ends up looking like. We'll end up with a situation here where we've got the nucleus in the center of both of the atoms. But what we get is, if the right-hand atom, if its electrons are being attracted towards the left nucleus, what that's going to do is drive the electron cloud kind of away from it, so it distorts it. You get a situation kind of like this, whereas the other one's going to look more distorted in this fashion. So you get a polarized electron cloud. What do I mean by a polarized electron cloud? It means this right-hand side over here on both of the molecules, I'm going to put like 3 partials here because it's just a teeny tiny baby partial charge. I'm sorry, it should be a partial positive on that side. And over here where it's a little more electron dense, you're going to get a very, very small partial negative. On this atom, again, over here, where you've got more of the electron cloud, a very partial negative, and over here, a slight partial positive. So you're going to get an attractive force. You've induced a dipole. That's why it's called induced dipole, induced dipole. You kind of induced a dipole on each other. And so you do get a kind of like I said, a polarized cloud and a slight attraction. Now, the bigger the atom is, the more of these London dispersion forces it's going to have. Because think about it, the bigger the atom is, the less, if those electrons are way far out there, they're not going to be attracted as much as electrons that are close into the nucleus. So if they're way far out there, it's going to be way easier to move them around. I think of them as being wobbly electron clouds. It's going to be easier to polarize them. They become what we say in AP and call it as more easily polarizable. So the bigger the molecule is, as it gets bigger and bigger, the higher the boiling point's going to be. It's going to be held more strongly together because it's got a stronger positive-negative attraction. And the halogens are perfect. If you look at the halogens, fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. And that's a perfect example of these London dispersion forces because they're all diatomic. They're all non-polar, and therefore the only thing they've got going for them is the London dispersion forces. The bigger they get, iodine down here is really big. It's really much easier to polarize its electron cloud, so it's going to have a stronger negative and positive charge, and it's going to be attracted more. That's why it stays a solid. It's attracted a lot. Fluorine, on the other hand, is a gas because its atoms aren't attracted very strongly. Its molecules aren't attracted very strongly because they're so small. Their cloud's not easily polarizable. So you get a much smaller partial negative and partial positive. So that's for our non-polar substances. If you're non-polar, this is all you've got. Dipole-dipole interactions are caused by the attraction of polar molecules to each other. Dipole-dipole is for polar molecules, once again. So let's say that you have this molecule that has a positive and negative end. It's going to be attracted to another molecule that has a positive and negative end, which is going to be attracted to another one with a positive and negative end, etc., etc. So you're going to get a relatively strong intermolecular attractive force from these positive, negative poles, these dipoles on these molecules. Again, this is for polar molecules. It's similar to an ionic bond, like it says down here, but much weaker since we're only talking about partial charges. Only talking about partial charges. So what's our final one? It's like polar, dipole gone psycho. This is called hydrogen bonding, and I think of hydrogen bonding as the meaning of life because hydrogen bonding is what causes water to have all of its weird characteristics. We'll talk way more about that in the next unit. But what happens with this is you have a situation where you have either that hydrogen is bonded to either fluorine, oxygen, or nitrogen. Fluorine, oxygen, and nitrogen are very highly electronegative. So they're pulling electron cloud towards them like no other. So you get a situation where these hydrogens right here are very electron deficient. They only had one electron to begin with, and oxygen's pulling its fair share, way more than its fair share of that electron, and it's leaving hydrogen feeling almost electronless. So what does it do? And it's very important to realize that it does this with a neighboring water molecule. It will hook up and attract to the oxygen side, the negative side, partially negative side of another water molecule. This attraction between two different molecules, hydrogen to the negative end of another molecule, is called the hydrogen bond. Now the hydrogen bond is very strong. It's the strongest of the intermolecular attractive forces. It's about 5% the strength of a covalent bond. Now remember where I'm drawing this in green? That's like if you tried to take those hydrogens off of that oxygen, that'd be like ripping your arms off. So that's a covalent bond. A hydrogen bond is an intermolecular between molecules attractive force, and therefore it's not nearly as strong, but again it does hold the water molecules together quite well. If you've ever, if you pour water out on a table, it's going to be in a puddle. If you watch raindrops falling down your windshield, they're going to be in droplets. So it does cause some pretty significant attractive forces. Now, covalent compounds, then, because of these intermolecular attractive forces, have different characteristics than the ionic compounds. They're composed of nonmetals. Remember, ionic compounds are metal plus nonmetal. They are solid, liquid, or gases at room temperature based in general on their molecular weight. Now remember, our ionic compounds were pretty much, they're solid crystals. Those ionic crystal lattice structures are very, very strong, and it takes a lot of energy to break them apart, which is why ionic compounds have really high melting points. Covalent compounds have low melting points. Remember, all you're doing with take some water molecules here, all you're doing when you're trying to melt or boil a quantity of water is breaking down this red part, this intermolecular attractive force. You're not trying to rip off the ears, okay? So it doesn't take as much energy. Now, they're horrible conductors of electricity in any state. Remember, we could get ionic compounds to conduct electricity if they could move, if they were solid or melted, because they have charges, they have ions in them. So as soon as you get them started moving, you've got those moving charged particles, you've got electricity being conducted. But think about it, covalent compounds don't have ions. If there are no ions, if there are no charges, it doesn't matter how much they move, they can't conduct electricity. So no charged particles means no electricity being transferred. Now, one thing I want you to be able to do on the worksheet today is to be able to determine the predominant intermolecular force, the predominant IMF, it's sometimes called, present in these following elements here. You're going to place an X through any substance that does not have intermolecular attractive forces. And down here are kind of some rules to go by on how to get started. The first thing you want to check for is if it's ionic or molecular. Because if it's ionic, it's not going to have any IMFs, and you're going to put an X through it right away. So remember, ionic is something that is a metal plus a nonmetal. So any of these up here that is a metal plus a nonmetal is going to be ionic, and it's not going to have any intermolecular attractive forces. So if you look through here, hopefully pause it for a minute and find that one. There is one up here, and it's lithium bromide. Lithium is a metal, bromine is a nonmetal, so that's an ionic compound. So it will not have any IMFs, so that has nothing, okay? The next one you're going to look for is hydrogen bonding, because you want the predominant one, and hydrogen bonding is the next strongest one. So look at the one that's hydrogen bonding. Look for one that's hydrogen bonding, which has to have hydrogen bonded to F, O, or N. Now, PF3 and CF4, those do not have hydrogen bonding. I've had people tell me before that something like NCl3 would have hydrogen bonding. Well, not that one. Let's see. NCl3, because it's got nitrogen in it. But you can't have hydrogen bonding if you don't have any hydrogen. So it's got to have hydrogen plus F, O, or N. And if you look up here, you'll see that this one right here has the hydrogen, and that hydrogen is bonded to oxygen right here. Therefore, this is going to have hydrogen bonding. And if it has hydrogen bonding, that's the strongest. So you are going to automatically put down hydrogen bonding for that one. The next thing you have to do for any remaining structures, after you've picked out the ionic ones and X'd them out, and after you've found the ones that are hydrogen bonding, you're going to have to find and draw the structures for the rest of them and decide if they're polar or not. So for PF3, if I draw the structure of PF3, count up the valence electrons, I end up with this structure. I have phosphorus with fluorines around it. Give myself a little more room up here. Fluorines around it. It's going to have pairs of electrons around all of the fluorines, and then when we get done, we're going to have an extra electron pair left over still, and that one's going to go on phosphorus. As soon as we put that lone pair on phosphorus in that tetrahedral shape, we've got an unbalanced charges, so unbalanced distribution of charge, and so this one is going to be polar. As soon as we say it's polar, we automatically know that this is the dipole-dipole interactions. Dipole-dipole interactions for our PF3. So that's going to be our answer for PF3. I guess out-of-box hydrogen bonding as well. Now CF4, when we draw CF4, it's going to end up looking like this. It's going to have carbon in the middle, and it's going to have fluorines around it. This time when we draw it, all of the fluorines will have lone pairs around them. But when we count up the electrons, we will find out that carbon doesn't have any. It's pure tetrahedral. As soon as it's a pure structure, pure tetrahedral, no lone pairs, we know it's nonpolar. And as soon as we know it's nonpolar, we know that it is London dispersion forces. So if you have your worksheet, this is how you're going to do that part of the worksheet.